Hello, this is Pat Hindle, editor at Microwave Journal. It's my pleasure to welcome you all to the session in our Technical Education webinar series on essential thermal-mechanical concepts needed in today's microwave circuit designs. Before we start, there's a few items I'd like to bring to the attention of our viewers. Today's presentation will be approximately 45 minutes long, after which time we'll hold a 15-minute question and answer session with our presenter. You may submit questions through our website at any time during the presentation through the Q&A box. All the questions will be addressed at the end of the presentation, and please use the Q&A box and the default setting for all presenters. Following the sessions, you will receive an email with a link to download the slides today. The presentation will be recorded and available for replay in the events section of the Microwave Journal website. It usually takes about 24 hours for it to be posted after today's event. Also, if you'd like to see more detail in the slides, you can click on the Enlarge button. Good design for thermal management of microwave PCB applications require a wide range of engineering understanding. It's advantageous for a designer to understand basic heat flow theory, microwave insertion loss, PCB construction, layouts, and high-frequency circuit materials properties. A designer well equipped with this information has more freedom to design trade-offs to optimize the circuit design for electrical and thermal performance. This webinar will present the basic concepts for heat flow as it relates to PCB technology and materials properties. I'd like to introduce today's speaker. John Coonrad is a Senior Market Development Engineer at Rogers Corporation, the Advanced Circuit Materials Division. John has been involved in printed circuit board industry for 27 years. The initial 11 years were spent in the flexible printed circuit board industry responsible for circuit design, applications, processing, and materials engineering. Following this experience, John supported the high-frequency rigid printed circuit board materials made by Rogers in regard to circuit fabrication, application support, and electrical characterization studies of all these materials. John is vice chair on the IPC D24C High-Frequency Task Group and holds a degree from Arizona State and Bachelor's of Science in Electrical Engineering. John has a series of videos online with Rogers giving you advice on different design techniques for PCB materials, and he's very well versed in this subject. At this point, I'll hand off the session to John.
Thank you. Good day, all. And I'm going to talk about the subject mentioned here, and really what it is, I'm going to be specifically talking about critical factors involved with thermal management of printed circuit board technology at microwave frequencies. And this is going to be a relatively fast-paced webinar, and the way I look at it is we're all pretty busy. If you're going to spend an hour of time listening to me, I really want to give you a lot of information. The outline is shown here, and I'm going to start off with just a basic concept of heat flow as it relates to printed circuit boards. And then I'm going to talk briefly about two different scenarios of printed circuit board thermal management. After that, we'll get into some of the laminate properties that are critical, and then I'll show some results of multiple experiments I've done regarding heat flow, temperature rise, and also have some thermal images that I think will be very descriptive. And then finally, I'll talk about aging characteristics of thermoset laminates. So with that, let's go ahead and get started and talk about some heat flow. So there's three different types of heat transfer: radiation, convection, conduction. In printed circuit board applications regarding thermal management, conduction is typically the issue that we're most interested in, even though radiation and convection can be involved as well. If you look at a very simple thermal model, and this is right out of a physics text, and it shows a single body that has a fixed temperature on one end very different than the other end. So you have a hot fixed temperature on one end and a cold fixed temperature on the other. Sometimes it's called a hot reservoir and a cold reservoir, and they're physically connected together by some kind of conductor that is very good for thermal conductivity. Then that's kind of the model that I'm going to start with. And it's assumed that this model is at steady state. So it came to a steady state and is holding steady, so to speak, and the energy going from the hot fixed temperature to the cold fixed temperature is heat flow. And the heat flow formula is shown. It's a very simple formula, actually, but it's really useful for thermal management issues. So H is the heat flow. Area is the area in contact between the thermal conductor and the hot and cold reservoirs. And then the T sub H, T sub C, or the delta T, that's really the temperature difference between the hot and cold reservoirs. and then L is just the length, the distance between them. How that relates to printed circuit board technology, I'm going to use the example of a microstrip transmission line circuit, and actually I'm going to use this throughout the presentation and also throw in a few others, but this is going to be the core of the matter. So for a microstrip transmission line circuit, there's a 3D view of what I'm talking about there, which I'm sure everyone's pretty familiar with, but essentially you've got two copper layers, a signal plane on top and a ground plane on the bottom, and they're separated by a dielectric material. In the cross-sectional view, kind of in the middle of the page here, you see the same circuit, signal plane on top, a gray area that's the substrate, and then another orange layer on the bottom, which is the circuit ground plane, and it's attached to the deep blue or the dark blue heat sink by a very thin layer that's a light blue, that's a TECA. TECA is an acronym for thermally, electrically conductive adhesive, and what's assumed here is that the circuit is acting as our thermal model, where the signal plane is the heat source. That's where the heat's being generated. And in reality, there's more to the story. But for a simple model, this is okay. And then the ground plane is assumed to have the same temperature as the heat sink. So it's the cold reservoir. The circuit ground plane and the signal plane is the hot reservoir. And what connects these together in a thermal sense is the substrate. So the substrate is acting as the thermal conductor, but it's really not that good for thermal conductivity. If you look at the numbers, which we will, the thermal conductivity of most substrates used in the printed circuit board industry are not that great. So it's acting as the function of a thermal conductor, but in reality, it's more of a thermal insulator, and that's some of the problem. So in general, for thermal management issues, having a higher H heat flow is good. So you want to increase heat flow. And having a higher heat flow essentially means the circuit's going to stay cooler, and it also lets you put more power through the circuit. Because really what it comes down to, for the maximum power that you can put on a circuit, what it comes down to is you cannot violate the maximum operating temperature of the circuit. So if you're able to increase heat flow and keep a cooler circuit, you can actually put more power through it. I'm going to talk about the maximum operating temperature and some details there a little bit later. So back to this heat flow formula that's really good to kind of keep in mind as you go through thermal management issues, and there's some relationships to consider, and some of it's pretty obvious. K is the thermal conductivity. The negative sign there is really just orientation of the coordinate system. But anyway, the K is thermal conductivity of the substrate in this case, and a higher thermal conductivity is directly related to H. So if you increase thermal conductivity, you increase heat flow, which is good. A thinner circuit also increases heat flow because L is the thickness of the circuit, and as you decrease that, then obviously it's inverse related to H, so you increase the heat flow. And then a wider conductor also is helpful, where you increase the area between the signal plane and the ground plane by having a wider conductor, and that also increases heat flow. So those are some of the trade-offs and things to think about as you're going through thermal management issues and looking at how the printed circuit board behaves as it regards heat flow. So there's two basic thermal management issues regarding PCBs. And the first one is just a device mounted on the printed circuit board, and the device that's mounted on the printed circuit board is actually generating the heat. And then the other scenario is when the printed circuit board is actually heating up because of applied power. So that's two different things to think about, and you have two different material considerations for those two different scenarios. So one scenario, the device is mounted on the printed circuit board, soldered to it, and it's generating heat. And then the other is the RF power is actually heating up the conductor, so you have trace heating or conductor heating due to RF power, and that's a little different scenario. So to begin with, device heating, if you were to look at my cross-section that I've drawn here, microstrip transmission line kind of, sort of, and it's got a device mounted on top, and in this case, the device is the active device generating heat is assumed, and it's also assumed in this drawing that the device has a ground plane at the bottom that can be used as a heat sink. So the device is actually soldered down to the circuit, and the circuit has something called a via form, where you have a lot of these plated through holes that act as a very good thermal conductor from the signal plane to the ground plane. And I've got some experimental data that I've done with this that you'll see makes a remarkable difference. The physics model I've been talking about for this isolated area is shown to the left here. And in this case, you have the hot reservoir, really the active device mounted on the signal plane, and then the cold reservoir is the ground plane of the circuit in contact with the heat sink. And then thermal conductor, in this case, is a really good thermal conductor. It's copper from the plated through hole. And then you have some insulation around it, and that's what the dielectric is acting like. So conductor heating is the other scenario, and conductor heating due to RF power is a little different. And in that case, you can't use the via farm idea because then the signal conductor is just going to be shorted to ground, and that's not going to work real good for a transmission line. The circuit properties, or circuit material properties, for this type of scenario is far more critical than the previous scenario. So the device heating scenario, thermal conductivity of the material is very important, but maybe the other properties are less important compared to RF heating. RF heating of the conductor, now you have insertion losses coming into play, and higher insertion loss means more heat generated. So now besides thermal conductivity, which is going to be very important, you also have things related to insertion loss like dissipation factor, copper surface roughness, frequency dependency, things like that. So what has been used, and I have some experimental data showing some of this as well, is a ground to coplanar waveguide instead of a microstrip, where the conductor, the signal conductor in the middle on the top copper layer is generating the heat by the RF power being applied to it, and you get some lateral heat flow from the signal plane to the adjacent ground planes on that same layer, and then the heat flow has the ability to go down the vias to the heat sink below, and it actually works pretty good for having a little bit better thermal management. Excuse me. So for laminate properties that are critical for thermal management, obviously thermal conductivity is a big deal. I'll talk some about dissipation factor. Smooth copper surface can be very advantageous. And then dielectric constant, which is usually not thought of in the case of thermal management, but it can be beneficial in a couple of regards. So for laminate properties that are critical, well, to tell you what, to begin with, let me switch gears and talk a little bit about MOT, because this is a really important topic. MOT is maximum operating temperature, and it is a rating that is supplied by Underwriter's Laboratory, UL. So when a fabricator makes a circuit, they generally make a circuit of multiple laminates and prepregs, and that goes through certain processes. They submit it to UL, and then UL does testing, and then UL comes back and tells them that circuit is rated to such and such temperature for MOT, and that's the maximum temperature that circuit can operate at. And any temperature at the MOT or less, then that's fine for the circuit to operate at indefinitely without degradation to critical properties. Anything beyond the MOT temperature, then it's all bets are off. Bad things are going to happen sooner or later. So not violating the MOT is the big issue here. And when people have asked me before, how much power, what's the power handling capabilities of a circuit, my answer kind of surprises them sometimes, and that is you can put as much power as you want through the circuit as long as you don't violate the MOT. As long as the circuit doesn't heat up enough to violate the MOT, that's your limit by how much power it takes to do that. And if you're running models, which I do a fair amount, and you really don't know what the MOT is of a circuit, a good rule of thumb is to use 85 degrees C as the rule of thumb for the MOT. So if you're comparing different models and looking at thermal models, and if you just don't know what the MOT is of a circuit, just assume 85 C is the highest temperature that circuit should achieve. So thermal conductivity, now we're talking about some material laminate properties. We sometimes abbreviate that as TC, and the unit is watt per meter per Kelvin. And mostly in the printed circuit board industry, most materials are not very good thermal conductors, actually more of a thermal insulator. There are some high-frequency materials just by their formulation that have better thermal conductivity. And as a rule of thumb, we generally say that about 0.5 watt per meter per Kelvin is a good number for what I consider good thermal conductivity or greater. And then copper, just to give you a reference, is really good, and that's about 400 watts per meter per K. So you can see copper is a fantastic thermal conductor, whereas most materials used in high-frequency printed circuit board industry are not so hot, or not so good, excuse me. Anyway, so I put in there some typical TC values of different materials used in microwave technology, and the high TG FR4 is used actually as hybrids sometimes. So sometimes a high-frequency printed circuit board has a combination of FR4 materials and high-frequency materials, so I included that here. But in general, you can see those type of materials usually have numbers about 0.3, sometimes a little less. Woven glass PTFE, which is used a fair amount in high-frequency applications, they're usually not that good for thermal conductivity, around 0.25 or so. There's some a little better, some a little worse. And then our Rogers 3003 material is a ceramic-filled PTFE product, and that's got a thermal conductivity that's considered pretty good at 0.5, and then 4350B and 4360G2. Both of those laminates are not PTFE. They're a thermoset system, and they are used at high frequency. And you can see their thermal conductivity is quite good at 0.62 and 0.8. And then the final product I'll talk about briefly is the 6035 HTC laminate. That was formulated specifically for very high power applications, and it's got the highest thermal conductivity that I know of on the market if you measure everything correctly. And it does extremely well and is used at very high power applications and very good for thermal management. Dissipation factor, that's a unitless type of effect. It's DF or tangent delta. That's really a property related to dielectric losses, and dielectric losses is a component of insertion loss. And essentially, if you have a lower dissipation factor, that means you can have a lower insertion loss. And lower insertion loss means you're going to generate less heat when RF conductor heating is involved. So having less heat, less insertion loss generates less heat. That's really important. Some of the DF values are shown here. You can see that the 6035 material is really good at 0.0013, and it also has extremely high thermal conductivity as well. So all around, it's formulated for really dealing with thermal management and high power applications. The copper surface profile, this is a concern related to insertion loss, specifically conductor loss, the component of insertion loss being conductor loss. And in this case, just to make things clear, the copper surface profile I'm talking about is really the copper surface that we bond our substrate to when we make a laminate. So it's the copper substrate interface of the laminate, and that surface is typically roughened purposely, and the reason why is because of the treatment there. The treatment is actually there for thermal stability as we go through a high-temperature lamination to make the laminate. And then also the roughness adds more surface area, which actually increases the bond and helps for bond. But unfortunately, the surface roughness also is a negative on the side of conductor losses, and a rougher surface will cause more conductor loss, which causes more insertion loss, which causes more heat to be generated. So we've done a lot of studies on these copper surface roughness, and I've got a reference at the end here I'll talk about a little bit. But in general, a smoother copper surface will generate less insertion loss and less heat. So dielectric constant, that's another material property that's usually not thought of in the sense of thermal management, but it can make a difference, and sometimes a big difference. So the thought here is if you're looking at different circuits and you're changing design from one circuit material to another, and you go to a lower dielectric constant material and you try to maintain the same impedance, what you need to do is widen the conductor to maintain the same impedance. The wider conductor will give you lower conductor losses generally, which means lower insertion loss, less heat generated. The other benefit is a wider conductor relates to the heat flow formula in area. A wider conductor actually increases the area, obviously, and now you have more area between the signal plane and the ground plane, and you have better heat flow, so the heat flow increases. So now I want to share some results, some experiments that I've been doing over the last several months, and just going through the agenda here on this portion of it. The first part I'm going to talk about an overview of the thermal testing I did, just kind of the setup so everyone understands what I'm doing for the actual testing. And then I'm going to show some results from device testing that we did where we actually heated a device and then we looked at the thermal profile of the circuits, and we used different materials with different properties. And then I did a lot of experiments looking at RF power heating a conductor and then using different materials and different properties. So the setup is shown here. And it's a pretty simple setup, actually. What we did was we had a water-cooled heat sink built, and then for the circuits to be tested, we had the circuits built. They're a very simple microstrip circuit, ground plane on the bottom, signal plane on top. You can see the signal plane in this case. And in this case, this is a circuit that was used for device heating. So in the middle of the signal conductor run, you see that black box there. That's really a simple 100-ohm termination resistor. And what we were doing was using DC power to heat the resistor to cause the device heating. Now, the circuit is bonded to this mounting plate by using a TECA. TECA is, again, thermally electrically conductive adhesive. And in this case, it's a new product Rogers has launched. It's called CoolSpan. And I've got a lot of testing on this. If there's any questions on that, please let me know. But I've got a lot of results on it, and I'm pretty excited about this new product. So the RF heating is using the same concept, but it's a simple microstrip transmission line. So the signal layer is just a single conductor going from, right across down the line there. And I have several power amps, and the one that I used here was centered at about 3.3 gigahertz, and I varied the power levels to look at different things in the experiments. So now looking at the device heating experiments and a little bit more about the setup. So one good thing about doing DC heating of a device, resistor in this case, is that it eliminates all the high-frequency variables. So now I don't have to worry about dissipation factor, insertion loss, copper roughness, frequency dependency, none of that. I basically just heat it up, and then I map thermally what happens. And what's nice about that is I'm really looking at the thermal conductivity of the material only. I'm not looking at high-frequency properties of the material. So that's a good thing. Makes models a little bit simpler. And the circuit designs that I've worked with are shown here. And the ground plane is below or into the page, and I'm looking just at the signal plane. The resistor has two terminals that's soldered left and right, and then the resistor also has a pad underneath it for a heat sink. And the design on the bottom is just a simple microstrip transmission line with the resistor being soldered to it that's not shown. And then the design on top is the same thing, except it has a lot of vias in there. That's what the little holes are. So I have several plated through-hole vias that are acting as a via farm. And in this study, all the circuits were the same thickness. They were all 20 mils thick and used the same thickness of copper, about 1.4 mils thick. And we did power testing at different power levels and also used the materials with different properties. And the next slide, if I can get to it here. Okay, this is some thermal images of this study. And it's looking straight down on the circuit, and the glowing part there is the resistor, actually, that's heating up due to the applied power. In this case, it's 4 watts of DC power. The upper left-hand picture is a woven glass PTFE, and you see there's a pretty good heat rise there, about 84 degrees rise above ambient. And then to the right is our 4350B laminate, and then below is the 6035 HTC laminate. And you can see the heat rise differences. So when you think about these materials, thermal conductivity is the big difference here. And in the case of the woven glass PTFE, the thermal conductivity is about 0.25 watt per meter per K. And the thermal conductivity of 4350B is about 0.64 watt per meter per K. And then the 6035 HTC is about 1.44. So there's a pretty big difference there. And you can see what kind of difference that makes on the heat rise as well as the maximum temperature that these circuits achieved. So now looking at a chart that charts this information with different power levels, DC power level on the bottom on the x-axis, and you can see the competitive PTFE, which is a woven glass PTFE, at all power levels was the highest temperature. And in each one of these data points, we did allow for the circuit to come to a thermal equilibrium before we took the pictures and made the measurements. But in general, the woven glass PTFE did what we thought it would do for thermal conductivity, and it is the one that's generating the most heat with the power supplied. And then you can see there's a pretty good step down to the 4350B, where it's running cooler at the same power levels, and 4360G2 cooler again. And that one has a thermal conductivity about 0.8 watt per meter K. And then finally, the 6035 HTC that's got the lowest thermal conductivity. And, of course, it remained the coolest with the different power levels. Now, looking at via farm versus no via farm, there's really a pretty big difference here. And in this case, this is a comparison showing the same circuits, same everything. The only difference is the circuit on the left was a circuit without a via farm, and the circuit on the right is a circuit with a via farm. And this is a little bit higher power than the last one that was at 4 watts. These thermal images are at 5 watts. But you can see the maximum temperature without the via farm is about 200 degrees F, and the maximum temperature we achieved with the via farm is about 109. So that's a huge difference. So, in fact, via farms really do make a big difference. Here's the same kind of graph I showed a little bit earlier, but now with via farms. And the x-axis is actually higher power than what we showed before. And what's interesting is the difference of materials is less now. So the difference in data is more compressed. But there still is a difference in thermal conductivity of the materials or the effects of that. So even though the via farms really do improve the thermal management a lot, having materials with higher thermal conductivity still helps a lot. So if you look around 15 watts or so, there's probably about a 10 degrees or so difference in temperature. And for thermal management issues that are critical, that's a pretty significant difference. So now looking at some of the experiments I did with RF heating, which I think is a little bit more fun. I've got a lot of pictures on that too. But so we had the same setup, and in this case, the first several images are going to be using microstrip transmission lines, and the applied power was at 3.3 gigahertz at different power levels. And to really get a good, accurate reading with the thermal imaging camera that I had to have everything the same emissivity, and what I did was paint everything a flat black paint and then have a way of measuring the emissivity and record that into the thermal imaging camera, and that gives me a really good, accurate reading. The problem is the black paint increases insertion loss because I'm spraying it right on the signal conductor, and now what I'm going to be showing you is what I consider a worst-case scenario because I added black paint to this thing, and I've actually increased insertion loss, which will make the heat rise more. But this study is good to compare different materials, though, at least, so it's a good comparison study. I don't really have time to go through this in much detail, but this is something kind of interesting that I ran into, and it's worth thinking about, and that is on these long circuits that I was testing, some of them 6 inches long, some of them 8 inches long. At 3.3 gigahertz, I have several waves on there, and a wave is going to have different energy levels by the phase. So you actually have hot spots and low spots across this circuit, but it's not very well defined, really because the conductor, the signal conductor, is such a good conductor. It actually spreads the heat pretty evenly. But you do have hot spots and low spots, and some of that's due to the wave effect, I think, and some of it's probably due to VSWR, would be my guess. Even though all these circuits at 3.3 gigahertz, I ensured that we had really good return loss, and I don't think the VSWR was much of an issue, but you never know for sure. So really the picture I'm showing here is a circuit that is a top view going from left to right, and the connectors are off the screen to the left and off the screen to the right. They were in-launch connectors, and you can actually see in this case the mounting screws, so to speak, of the heat sink. So there's a screw here, here's one, another one here, another one there. And just for reference, if you skip back to the slide that shows this configuration, these are the mounting holes I'm talking about. So it kind of orients what we're talking about here. So what I did in this case is actually look at the thermal profile across a line that was centered right down the signal conductor. And what I did on the rest of the study was actually rotate that 90 degrees and measure the highest temperature and zoomed in. And that's what the next slide shows. So the picture I previously showed to the left, and then what I actually did on the rest of the study was rotate it 90 and zoom in close. And that's what's shown to the bottom right. And you can see the conductor is there's a lot of heat there, obviously. But as you move away from the conductor, there's not much heat spreading out onto the surface of the substrate. There is some, but not a lot. So out on the surface of the substrate, it's about 74 degrees, and the center of the conductor is about 111 degrees. So what that's really telling me is there's a good amount of heat flow going from the conductor through the substrate into the page, down to the ground plane, and down to the heat sink below. And there's not too much heat spreading out onto the surface of the circuit, which is what is desired. Now, a good comparison here of two materials that are very similar, about the same thickness, just about the same dielectric constant, and just about the same thermal conductivity, but the only major difference is dissipation factor. So the picture on the left is a microstrip transmission line on 24 mil 4360 G2, and this is with 50 watts applied power at 3.3 gigahertz, and I'm showing the maximum temperature about 111 F. And then the circuit on the right is a very similar type of circuit, same conductor width, nearly the same thickness, nearly the same dielectric constant, nearly the same thermal conductivity, but you can see the dissipation factor is very different. So the dissipation factor of the 4360 G2 is about 0.0038, and the 3006 material is about 0.002. And from that, we have lower insertion loss, which means less heat's being generated. And in fact, you can see that by the maximum temperature, about 98.5 versus 111 degrees for the 4360 G2 material. Now, something that I thought was kind of fun is showing the same circuit with and without a heat sink. So this is a really good slide to show how significant a heat sink really makes a difference on the thermal management issue, which I think is intuitively known, but it's just kind of a fun slide to look at. So what I did was I used a 50 ohm microstrip transmission line, 10 mil thick, on Rogers RO4350B laminate, and I applied 85 watts at 3.3 gigahertz with no heat sink, and that's the bottom left picture. And you can see things got pretty toasty, about 369 degrees F in the center of the conductor, and there was a lot of heat spreading going off to the sides of that on the surface of the circuit, mainly because I had no place else to go. And then when you take that same circuit and attach it to a heat sink and put the same power through it, that's the right picture. And the picture on the right, you see a much different thermal image where the maximum temperature is about 105 and it's centered at the conductor. And as you move away from the conductor out on the surface of the circuit, it's only about 71 degrees. Now, what's interesting is the heat sink temperature was around 68 to 69 degrees for most of these studies. So the surface of that circuit is not that far off the temperature of the heat sink itself. And that's a good thing because that shows pretty good heat flow. The other thing is this is a thinner circuit than what we've looked at so far. So this actually has a shorter heat flow path. And again, if you have a shorter heat flow path, that means you increase heat flow, and that's what happens here is you actually get a lower temperature, even though it's thinner and probably has a little more insertion loss than some of the circuits we looked at so far, and more heat being generated. Actually, it's staying cooler because you have a shorter heat flow path and improved heat flow. So here's a quick matrix of some results that I got on the RF testing, basically the heating of the conductor with RF power. And this is only some results out of a lot that I did. And this is a good comparison between different things. And the first comparison you might want to look at is the ID for Circuit 1 compared to ID Circuit 2. And you can see they're really the same materials, and they are the same materials, exactly the same. The only difference is one's thicker than the other. So ID1, that circuit is using the 10 mil 4350B, and ID2 is using 4350B also, but 20 mil, so it's twice as thick. And as you go across, you can see the insertion loss is much worse on the thinner circuit, ID1, which makes sense. If it's thinner, you got a more narrow conductor to maintain 50 ohms, and in general, a thinner circuit's going to have more losses in general. But anyway, you can see what's interesting is the heat rise to the right. Even though the thinner circuit had more insertion loss, it did not have a higher heat rise. It actually had a lower heat rise. So the thinner circuit with the shorter heat flow path actually does better for transferring heat from the heat generated on the thinner circuit. And actually, the heat generated on the thinner circuit is probably more heat because you have more insertion loss than the thicker circuit, but it still remained cooler. And then looking at ID2 circuit compared to ID3, the difference there really is copper surface roughness. So this is 4350B 20 mil versus 20.7 mil 4350B low pro. So there's a slight difference in thickness there, about 0.7 mils difference. And there's also a slight difference in dielectric constant, so the conductor widths are just slightly different. But the biggest difference is really the copper surface roughness. So circuit ID2 has a copper surface roughness about 2.8 microns measured as RMS, and then the 4350B Low Pro has a 0.8 microns RMS, so it's much smoother. And you can see to the right of that, the insertion loss numbers show that as well. Oops, sorry about that. Let me get back to the slide. Okay, so the insertion loss numbers show that as well, where the circuit with the smoother copper does have the lower insertion loss, and in this case, the one with the lower insertion loss does, in fact, have the lower heat rise. And all things considered, it really should, because these circuits are very similar outside of the fact of having smooth and rough copper and difference in insertion loss. Now, the high-performance FR4, I put that in there as really a worst-case scenario because it's got everything going against it at microwave frequencies. And, of course, you wouldn't be using this material at this frequency normally, but just as an example. So it's got a dissipation factor that's really bad, so that's not a good thing for thermal issues. The thermal conductivity is also 0.25. That's not a good thing. The copper surface roughness is relatively rough. That's not good. Insertion loss, you can see, is, of course, pretty high, and it generated the most heat in this study. And then on the flip side of that would be the best-case scenario, ID5. That is looking at the RT Doroid 6035 HDC laminate, which really has a combination about the best-case scenario. You have a very low dissipation factor, 0.0013. That's considered very low loss. The thermal conductivity is extremely good at 1.44. And the copper surface roughness is considered relatively rough. So even with a rough copper surface, these other attributes still went out to have a relatively low insertion loss, and you can see the heat rise is very low. So now I wanted to look at some comparisons between microstrip and coplanar transmission lines, and I really wanted to look at the via fence idea. And when I started doing this study, I found I had some really funny results. And the reason why is when I sprayed black paint over everything, the insertion loss for a microstrip went up a lot, as you would expect. But the insertion loss for the ground to coplanar circuit went up a tremendous amount. And that kind of makes sense. So on the coplanar layer, you have a ground signal ground with a space between the signal and the adjacent grounds. And when that's filled up with a lossy material like black paint, it becomes really lossy. So really what happened was this was just not a fair comparison by using the black paint. So what I did is do some experiments with black bands. So I left the circuits as bare copper, and then I found the high temperature area of the circuits, and then I just put black bands in the area of the high temperature, and I made sure these black bands going across the circuit were no more than 1/10 the wavelength at 3.3 gigahertz. And it really appeared not to make any difference on insertion loss, which is good. So the testing on the next slides are much more real life, where the effect of the black paint really isn't coming into play. And I was able to do some measurements between microstrip and grounded coplanar and trying to check out if this via fence really is advantageous. And it turns out that it is advantageous. And here's a matrix of just some of the study. And again, we're using all the same material. In this case, it's all 10 mil thick, RO4350B. And the microstrip circuit is the ID number 6, and then a tightly coupled coplanar, grounded coplanar waveguide is ID 7, and loosely coupled is ID 8. And what I mean by loosely and tightly coupled is, in my picture in the bottom right there, the space between the signal conductor width and the space of the adjacent grounds. If it's tightly coupled, then I'm saying that space is very small. If it's loosely coupled, that space is large. And the dimensions are actually shown on the 4th row over. And so you can see that there's an insertion loss difference. And that's the row next to just about to the far right, insertion loss. And the microstrip and the loosely coupled grounded coplanar waveguide have just about the same insertion loss. And that's really because it was very loosely coupled. And then the tightly coupled grounded coplanar waveguide did have more insertion loss, and that's because as I moved the space closer together, I had to narrow the signal conductor to maintain 50 ohms, and a more narrow conductor generally means more conductor loss and more insertion loss, and means more heat being generated. So in this case, what happened was the loosely coupled grounded coplanar waveguide had the lowest heat rise, even though it had the same insertion loss as the microstrip. It still had significantly lower heat rise, so that says that via fence trick really does work. So there is some lateral heat flow from the signal plane or the signal conductor on the coplanar plane to the adjacent ground planes, and then the vias are used to bring the heat to the ground plane below. Now, the tightly coupled, that had the higher insertion loss, and even though the vias were closer to the signal, that benefit of the vias being closer to the signal did not outweigh the amount of heat being generated by more insertion loss, unfortunately. So the next few slides are some fun things about filters, I think. And this one's using a different power amplifier. This is a power amplifier that's around 2 gigahertz, and I'm able to get up to 30 watts. And in this case, it's a simple microstrip edge-coupled bandpass filter that's centered at 2 gigahertz. And you can see the design. This is the top view of it. And this particular design was pretty lossy, mainly because I sprayed black paint all over it. And so the top image here is showing what the top thermal image is showing what the bandpass filter looks like when 30 watts is applied in the center of the bandpass frequency. And you can see the different resonator elements lighting up with different temperatures. And what's interesting is if you change that from 2 gigahertz to 2.1 gigahertz, still within the passband, you'll see different resonators come to life and be more active. So as you move around in frequency within the passband, you can actually see the different resonators heat up and cool just by how active they are at these different frequencies, which is really interesting. And then, as a sanity check, I decided to adjust the frequency into the stop band, so getting away from the passband area of the filter, and see what kind of thermal image I got. And that's the bottom left image. And sure enough, element 1 lit up with some heat, and then element 2 has got some heat, but I think it's really just through conduction. And then the rest of the filter pretty much is shut off, and that's what it's supposed to do. So in the stop band, you should not let energy through the filter, and that's pretty much what it did, and it shows it thermally. So I did the same thing with my other power amp that's a little bit higher frequency and definitely higher power. And in this case, I'm showing two different circuit materials with the same filter design, and there's pretty big differences of these materials. The Rogers 20 mil 4003C laminate, that's used in a lot of high-power applications, and it works really good at that. But if you want to get the next level advantage, then the 6035 HTC is shown to the right, and you can see there's a pretty big difference in temperature. And there's also some of the properties shown here below the thermal pictures. So the 4003C and the 6035 HTC have similar dielectric constant, but outside of that, they don't have similar dissipation factor, where the 6035 HTC is much lower loss, and the 6035 HTC definitely has a lot higher thermal conductivity, even though the 0.64 watt per meter K for thermal conductivity of 4003, that's considered very good, and this material is used in a lot of high-power applications. So let's look at another comparison, and again, looking at some filters. This is a little different filter. This is a hairpin bandpass filter, again, microstrip. And in this case, I'm looking at the difference between bare copper and ENIG. So ENIG, electrous nickel immersion gold, that's a finish that is used a lot in the industry, and it's a very good finish. However, just by the nature of the beast, nickel does cause more losses because nickel is about 1/3 the conductivity of copper. And that's exactly what this is showing. And this is now the exact same materials with the exact same design, the only difference being the circuit on the left thermal picture is using bare copper, the circuit on the right is using ENIG plating, and you can see a remarkable difference in the maximum temperature of 152F with bare copper and 262F with the ENIG plating. And then just as a sanity check, I took a couple of screenshots of these filters in frequency domain with my network analyzer, and you can see that they were actually pretty well-behaved filters. So I had return loss in the passband around 17 or so on both of them. And then in the passband area, they had pretty good response. The one with ENIG had more losses, of course, and you can see that. Also, there's a little bit more, it's not as quite as selective, so the skirt's a little bit curved, and that kind of happens sometimes, and you have more losses as well. But in general, this is really showing these two filters were pretty well behaved for filter performance. So now I want to talk about a topic that came up in our last webinar, and that was what happens when a high-frequency circuit material is subjected to high temperature for long periods of time. And in the question and answer session in the last webinar, I answered that, but I answered it pretty quickly. And the more I thought about that, I wanted to put more information in here because this is a pretty important topic. So really what it comes down to is a reality check. Everything on Earth changes as it ages, and printed circuit board materials are no different. And I do get calls from time to time that people ask, do printed circuit boards change as they age? And it's like, well, yeah, sure, everything does. But in general, thermoplastic circuit materials age better, or more gracefully, I suppose, than thermoset materials. And that's just kind of the nature of the material. And then just kind of for fun, since I'm walking around with a thermal imaging camera in the middle of a desert, I decided to hop in my car and take a picture of my steering wheel and the dashboard, and that's what this picture is, and it's kind of a neat picture. But and this is not that hot of a day for us. This is only about 105 degrees outside, and we get a lot worse than that. But anyway, the steering wheel is about 160 degrees F, and the dash behind there is about 180. So I guess that should be no surprise to anyone that being subjected to that heat for a long period of time, years, my dash started getting cracks in it. So unfortunately, that's the same with everything else, including printed circuit board materials. When they're aged for a long period of time, something's going to change. So a quick summary of different things to think about regarding thermoset high-frequency materials and what goes on during the aging process. So as the thermoset material ages, the exposed substrate will oxidize, and that's assuming you have oxygen present. If you have a circuit out in outer space somewhere, it's not going to oxidize. But anyway, elevated temperatures will actually increase the speed of the aging effect, or basically increase the oxidation. And given enough time, as these thermoset materials are aging and becoming more oxidized, they do get to a point where they kind of come to equilibrium, and the oxidation rate slows down to just about zero. So you get to a plateau where all the change is done. And there's a lot of different thermoset systems out there, different thermoset resins with different additives. And really what that means is not all thermoset materials behave the same. Different formulations can age different than other formulations. And the bottom line is, from many, many studies we've done, and I'm willing to share, we find that the aging effect is very much frequent, or is very much design dependent. So it's very much dependent on the circuit design itself. And let me give you an example of that. So what I'm talking about is looking at different designs, and the assumption is the circuit had been at long periods of time at very elevated temperatures, and the circuit was not violated for MOT, and there is oxygen present. So in general, with all those assumptions, a strip-line circuit has pretty much minor or no perceivable electrical difference over very long periods of time, mainly because copper is really good at protecting the substrate from oxidizing. So the substrate just can't oxidize except maybe at the edges, and it takes a long time for it to work in from the edges. So strip line, you really don't see much difference. Microstrip circuitry, you can see more differences in strip line because, of course, you have some exposed substrate on microstrip circuitry. Now, it depends on what kind of circuitry. So for transmission lines where most of the fields are between the signal plane and the ground plane, the dielectric there is actually protected by the copper, so that dielectric really isn't changing much for aging or for oxidation. Now, the fringing fields at the edge, that's going to pick up on some of the material at the edges of the conductor, and that will make a little difference, but not much. So most of the microstrip circuitry that really doesn't change much with long-term aging is like transmission lines, stubs used for impedance tuning, stepped impedance type of features, things like that. But the features that are more susceptible would be edge-coupled, kind of like the slides I showed a little bit ago with edge-coupled bandpass filters. And the reason why is because now you have these conductors with a space between them, and there's fields in there, and those fields are using the exposed substrate that has possibly oxidized over time with accelerated temperatures. So the bottom line is the copper does protect the substrate, and when you have designs where the copper is not protecting the substrate, that's more susceptible to some changes. Now, worst-case scenario is etching all the copper off and then do testing, which we've done on numerous occasions. And I'll give you a quick slide on one case that we did that. And this test is really not that aggressive. It's a common test that a lot of the OEMs are interested in sometimes, 85-85, which is 85 degrees C and 85% RH. It's using 20 mil thick material, and it's comparing our RO 4835 material to a competitive material that supposedly behaves the same, but I can tell you for thermal aging it sure doesn't. And there's a few other things I could talk about, but I won't. There's also something to think about here is the 4835 material is the same thing as 4350B laminate, except the 4835 material has a slight formulation difference in how it oxidizes and ages. So it ages much better than 4350, which actually 4350 ages very good, but 4835 does about 10 times better. So getting pretty close to the end now. Rogers materials, they've been used obviously over the years in a lot of demanding applications, and I mean a lot of applications, and we generally do not see an issue with the oxidation. So this oxidation effect and aging effect is a pretty rare effect, thankfully. But however, when this oxidation is around and should be considered, realize that it is very dependent on the design, the application, and the end-use environment. So we strongly recommend that our customers evaluate each material and design combination to determine the fitness of use over the life of the end product. And we most certainly want to help with that. And we have a lot of data we can share, but you've got to realize our data is usually testing raw substrate, and that's not really related to your particular design or application. So what it comes down to is just the engineers need to do their homework and really evaluate that the material is the right material for the application. So with my last slide, I'll give a little plug to our Technology Support Hub. We're pretty proud of this. We got a lot of good information here, I think. But if you get on our Technology Support Hub, you have access to different calculators. We have a microwave impedance calculator. We have a Raj mobile app that you can get. We also have electrical and thermal calculations. We have the ability to ask an engineer questions, and then a lot of our technical papers we present at trade shows are there, also different technical articles, many of which are for Microwave Journal, actually. So with that, I've given a reference here for the copper surface roughness, if someone's interested in that, and how copper surface roughness affects insertion loss. But with that, I think I'm ready for some questions.
Great. Thank you very much, John. Excellent presentation as usual. We'll jump right into the Q&A here. The first question is the MOT for ambient or junction?
That is what I would consider junction, if I'm understanding the terms right. But MOT is really the maximum temperature that the circuit can get to and maintain that temperature actually indefinitely without degradation to the performance of the circuit. So as long as the circuit is heated to the MOT or less, it can stay at those temperatures indefinitely. Once you violate the MOT, then bad things happen and the circuit performance changes.
Okay, that makes sense. Next question, did you measure the time constants as well?
We did that on a previous study a few years ago, and this recent study I did not. And really good question. Unfortunately, I can't talk to it very well right now, basically because of memory. I just don't remember what we got out of it, but we did do that on a study several years ago.
Okay, where is the temperature measured in the experiments?
It's really measured at the hot spot of the circuit, and I didn't explain that very well, and I apologize, but when I looked at these different circuits with different material properties, and one of them being dielectric constant, if I'm testing the RF heating of the conductor on a circuit that's got a dielectric constant of 3 as compared to a circuit that's got a dielectric constant of 6, I actually see something different for the heat patterns. And because of that, I went to the highest heat source away from the signal launch, because the signal launch was the highest heat source area usually. But once I got into the body of the circuit that was on the heat sink, then I went to the highest temperature area of the circuit, and that's where I measured. And that highest temperature of the circuit was different for different circuits, and I think it has to do with how the waves were on the circuits with different dielectric constant.
Okay, next question, were you able to model this result with FEA?
No, I was not. I don't have a good FEA software for thermal modeling. We've got a thermal modeling software that is a good software for, I'd call it ballpark type of measurements, and it's really based on a lot of empirical data that we've collected over time on different scenarios. So I did not have a good thermal FEA software to compare it to, unfortunately.
Okay. As the circuits age, does their thermal conductivity change? If so, by how much?
Yeah, it does, actually. There's a lot of properties that actually change as the laminate changes, and what's kind of ironic is as the laminate ages, generally the thermal conductivity actually increases a little bit. And it could be because the cross-linking of the thermal set is becoming more tightly cross-linked. But there is a little difference in thermal conductivity. It's not a significant difference, but there is a little difference. But as strange as it may be, it's actually a little bit of an improvement.
Okay. What frequency is the 60-35 insertion loss specified?
That would have been 3.3 gigahertz in this presentation, even though I've done testing all the way up to 50 gigahertz on that material. But for this presentation, it was just at 3.3 gigahertz.
How about the multi-layered circuits using 4350 materials?
Yeah, there's, well, we see a lot of different multi-layer circuits using 4350, and a lot of them are hybrids where they will have FR4 layers combined with 4350, and what they're doing really is probably a cost thing where you do not need the high frequency performance, you use FR4, and maybe those are the control circuits or maybe power circuits or things like that, but the high frequency part of the multi-layer printed circuit board would be used in the 4350. So 4350 is used in combination with a lot of different materials, and sometimes it is with FR4 and FR4 prepregs and laminates and things like that, and then sometimes we also have 4350 be used in combination with other Rogers materials, like we've seen some applications combining the RO3003 materials, which is even lower loss, with the RO4350, and we have very good results there. We have a really good technical support service team, so whenever it comes to circuit fabrication issues, I usually like to get those guys involved because they pretty much live this 24/7 for dealing with different circuit builds.
Okay, next question. Is there a formula for the temperature effect of surface roughness and insertion loss?
I'm sorry, say that again?
Is there a formula for temperature effect of the surface roughness and insertion loss?
Wow, that's a really good one. Not that I know of specifically for that. There are several different models for copper surface roughness, and people have been dabbling with that since 1949 with Morgan. So there's something called a Morgan rule that is used in some of the Hammerstedt and Jensen equations that is a multiplying factor by the conductor losses. So you would determine the conductor losses, and then you use this multiplying factor that is trying to account for the copper surface roughness increase in losses. But over time, it was found that the Morgan rule was not very accurate at higher frequencies and mathematically saturates and blah, 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 different things. So there's other models out there now. Gross has a model. Hooray has a really good model that's being used in HFSS now. And in general, those are all models related to insertion loss specifically, but not to the thermal side of it. As a general rule, as you have more insertion loss, you have more heat. But I don't know of a good formula specifically for heat and the copper surface roughness.
Yeah, I definitely see it. It's in the models for the insertion loss, like Sonnet software and other ones, HFSS.
Right.
Okay, next question. If you exceed MOT while the circuit is not operating, is there an operational degradation in performance?
I didn't catch all that. Say that again. I'm sorry.
If you exceed the MOT while the circuit is not operating, is there operational degradation in performance?
Yeah, there actually is. Even though it's not operating, if it's above the temperature of the MOT, there's mechanical things going on. So the interface between the substrate and the copper, what can happen, depending on the material, there's a lot of things that can happen. One thing that can happen is you can have oxides build up between the substrate and the copper, and those oxides actually degrade the bond or the adherence between the copper and the substrate, and that can make a little difference. So even though it's not active, if it's just stored someplace above the MOT, that actually can make a difference on the properties of the circuit.
What's the difference between the thermoset and the TH plastic PCB materials?
Well, I guess really in the high-frequency industry, those are the two main types of materials used as a general classification. There's the thermoplastic and thermoset. And the thermoplastic are a lot of times PTFE or something like that, and they're very soft. They don't have a glass transition temperature. And just by their nature, they generally have lower dissipation factor, but they also have other issues, sometimes thermomechanical issues like the coefficient of thermal expansion. For the PTFE materials, a lot of times that property is not real good, where the circuit will expand and contract a lot physically as it's being heated and cooled, where a lot of the thermoset systems do not have that issue, but the thermoset systems are generally not as low loss as the thermoplastic systems. So there's a whole bunch of differences when you really get into details. But you can do things with the thermoplastic systems like we did in the case of the 6035 HTC. That's really a modified PTFE. And even though it's thermoplastic, if you do the right things with the ceramic fillers that we did, you can get very high thermal conductivity, and also you can get very well-behaved coefficient of thermal expansion. So the difference between a thermoset and a thermoplastic for used in the high-frequency industry, there's actually a lot of different properties that are different. I guess the biggest difference that really just comes to mind on a molecular level, the thermoset materials have a defined T sub G, or a glass transition. So once you get to a certain temperature, the material actually on a molecular level changes. And in the thermoplastic material, as you go higher and higher temperature, it just basically gets softer and softer. It doesn't have an abrupt change like the T sub G does in a thermoset.
Okay, we have one last question here. How thick is the paint that you're using, the black paint? Maybe you can tell us a little bit about that.
How thick was I didn't get all that. I'm sorry, say again, please.
The black paint that you used for the thermal imaging.
Oh, yeah. I tried to control that the best I could. And I tried different experiments where I timed myself as it's spraying across the surface and different things and trying to maintain the same thickness on everything. Because that's really a good question, because if you have thicker black paint on one circuit than another, then you're actually tainting your results, because one's going to have more loss than the other because of thicker paint. So in this case, the black paint that I was shooting for measured about 1.8 mils thick on the average, and I wasn't really good at controlling it. It's about 1.5 to about 2.2 or so is what I was hitting around. But I tried to control it the best I could, but it's a really good question, because if that black paint thickness varies much, it will make a difference on insertion loss.
Okay, great. I think we've just about timed it right here. We went through the questions. Please visit the Rogers Corporation website, especially their Tech Hub, if you would like more information. And John, thank you very much. Excellent presentation as always, and we appreciate everybody for listening today. Please, one reminder that the presentation will be emailed as a downloadable link in the email to follow up to the session, and the recorded session will be live in about 24 hours on the Microwave Journal website. Thanks for listening today.